In this video, I will answer the questions in Exam 2 of Chemistry 473 in Spring Quarter 2021. I will skip question 1. Question 2. Which of the following transition metal complexes are low spin? First, let's look at the ligands. The cyanyl and carbonyl ligands are strong field ligands, so A and B are correct answers. And then let's look at the transition metal center. Tungsten is a 5D element. Rhodium is a 4D transition metal element. The 4D and 5D transition metal complexes are always low spin for two reasons. One, 4D and 5D orbitals overlap with the ligands better than 3D transition metals. Because 4D and 5D are more diffuse, they can overlap with the ligands better. Reason 2. 4D and 5D electrons feel less repulsion from each other than the electrons in the 3D orbitals. And thus, in the 4D and 5D transition metal complexes, the electron pairing energy is smaller. So both reasons result in the LFSE being much greater than the electron pairing energy in the 4D and 5D transition metal complexes. So for that reason, B and D are correct answers. So again, because of the ligands, A and B are correct. Because of the transition metal center, B and D are correct. So A, B, and D. Now let's look at C. Bromido is a very weak field ligand. Reason 1. Reason 2, this is tetrahedral. And delta T is only 4/9 of delta O. So that's why the LFSE in this case is much smaller than the electron pairing energy. This is gotta be the high spin case. Okay, two reasons. One, the ligand is a weak field ligand. Reason 2, this is tetrahedral. The magnetic moment of this transition metal complex is how many in mu sub B? This is pretty simple. Chromium in this case has an oxidation number of 3, therefore there are 3 D electrons, and then the square root of 3 times 5 is 3.8. Done. The equation is the square root of n times n plus 2 times mu B, where n is the number of unpaired electrons. In this case, n is 3. Question number 4. Rank the following transition metal complexes in the order of increasing LFSE. So first, let's look at the ligands. Cyanyl, amine, cyanyl. So cyanyl wins. And then look at the transition metal. This is cobalt is 3D, rhodate, rhodium is 4D, so rhodium wins. So this hexacyanyl rhodate has the largest LFSE, followed by this cyanyl and cobalt. Let's select the correct answer. Okay, right here. Rhodate has a larger LFSE than cobalt. Cyanyl has a larger LFSE than amine. But why do we call this cobaltate and this rhodate? It's just because when you have 6 cyanyl ligands, there's 6 minus charges, and then there's 3 plus charges on the transition metal. Overall, it's still an anion. When you have an anion in an ionic transition metal complex, you need to have this ATE in the end. That's just the nomenclature. Question 5. Find the complex with the largest LFSE. So cobalt, 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 right? But then look at the oxidation number. When we have a higher oxidation number, we have a stronger attraction between the metal and the ligands. Stronger overlap, larger LFSE. And then we compare amine and aqua. So amine is the stronger ligand. This is because when you look at aqua ligand, it's just water. So water has two lone pairs, and one lone pair is used to form a bond. The other lone pair actually can be donated to one of the empty d orbitals of the transition metal center. Actually, that make this aqua ligand a weaker field ligand than amine. Question 6, Young-Taylor effect. So first, I want to give you a brief summary about the Young-Taylor effect. When you have 1 or 3 electrons in the Eg orbitals of a octahedral transition metal complex, you have the strongest Young-Taylor effect. Again, 1 or 3 electrons in the Eg orbitals. Or when you have 1 or 2 or 4 or 5 electrons in the T2G orbitals of an octahedral transition metal complex, you have a weak Young-Taylor effect. All right, this is because the ligands are pointing directly to the dz squared and dx squared minus y squared orbitals. So it's stronger Young-Taylor effect when you have 1 or 3 electrons in the Eg orbitals, but weaker Young-Taylor effect when you have 1 or 2 or 4 or 5 electrons, d electrons in the T2G orbitals. Okay, so if you have 0, 2, or 4 electrons in the Eg orbitals, then no Young-Taylor effect there, right? When you have 0 or 3 or 6 d electrons in the T2G orbitals, even distribution of electrons in the T2G orbitals, no Young-Taylor effect. Okay, that's the brief summary. So now we can easily answer this question. When you have high spin D4, we have 1 electron in the Eg orbital. So this results in a strong Young-Taylor effect. High spin D5, no Young-Taylor effect at all, because you have 3 electrons in the T2G orbitals. You have 2 electrons in the Eg orbitals. You have just the same number of electrons in the 2 Eg orbitals. You have the same number of electrons in the 3 T2G orbitals. No Young-Taylor effect. Low spin D4 with a weak Young-Taylor effect. Okay, low spin D5, same thing. Yeah, a weak Young-Taylor effect. Because again, we're talking about the T2G orbitals. They are not pointing directly to the ligands. Which of the following transition metal complexes has the weakest Young-Taylor effect? All right, actually, this is pretty easy. If you know chromium 6 has 0 d electrons. When you have 0 d electrons or 10 d electrons, you have no Young-Taylor effect at all. So that's the weakest. There's another situation. What if you have a high spin D5, 0 Young-Taylor effect as well? Question 8. It's also about Young-Taylor effect. When you have hexa aqua copper 2, there are 9 d electrons. That means 3 d electrons in the 2 Eg orbitals, right? So that breaks the OH symmetry. It becomes D4H. For this atomic term, L equals what? S equals what? This 3 is the spin multiplicity. The spin multiplicity is equal to 2s plus 1, then s is equal to 1. L equals 4, because when you have S, P, D, F, G, L is 0, 1, 2, 3, 4. So 4 and 1. All right, so over here you just need to be familiar with the spin multiplicity and with the symbols for this angular momentum. Question 10, iron 3 plus, that means we have 5 d electrons, and if we just need to determine the ground term, it's pretty easy. We just put the 5 d electrons in 5 different d orbitals while maximizing the spin. So let's say 5 alpha spins, and then we can easily compute S. S is 2.5. 2s plus 1 is 6. So the spin multiplicity is 6. I think this is the only answer with a spin multiplicity of 6. Okay, now let's look at this symbol S. This is because we have 5 electrons with M sub L being equal to -2, -1, 0, 1, and 2. If you sum up -2, -1, 0, 1, 2, you get 0, right? So L is 0. If the sum of M sub L is 0, L is 0, then the symbol is S. Again, we're talking about S, P, D, F, G. Unfortunately, the letter S is used for the symbol here, and S is also used for spin quantum number. They are two different things. And this 6 is supposed to be in superscript. Question 11. Okay, in this case, we're going to name this anionic transition metal complex and determine its structure. It's a little tricky because very often when we see, for ligands, we say tetrahedral, but in this case, this is gold 3+. And if you look at your periodic table, gold 3+ has 8 d electrons. All right, so when you have a 4d or 5d transition metal center with 8 d electrons, no-brainer, it's square planar. So in this case, we'll just choose this tetrachloride aurate 3 with a square planar structure. All right. By the way, it's pretty easy to calculate the oxidation number here. Each chloride bears a negative charge, so this aurate or gold has an oxidation number of 3. It's named aurate because this is an anionic complex with a negative charge. Question 12, europium. Determine the ground term for europium 2+. It's for F7. We have 7 electrons in the F orbitals. Again, it's actually pretty easy to determine the ground term because you can just maximize the spin. S, the spin quantum number S is equal to 7 times 1/2. That's 3.5. Then the spin multiplicity is 2s plus 1, which is 8. All right, and there's another simple equation. The spin multiplicity is the number of unpaired electrons plus 1. We have 7 unpaired electrons plus 1, that's 8. Okay, and then this symbol S because M sub L of this 7 F electrons are -3, -2, -1, 0, 1, 2, and 3. When you sum it up, you get 0. Question 13. The UV-vis spectrum of a D2 transition metal complex. So when we have a D2 transition metal complex, when we look at its electronic transition, the first 2 bands are delta O and delta O plus 15B. So you can just look at my lecture notes and look at some examples in either the lecture videos or in the homework. Delta O is 20,000. Delta O plus 15B is 32,000. Also, you can just use Tanabe-Sugano diagram and the theoretical basis of the Tanabe-Sugano diagram. All right. I want to talk about the physical meaning of B. B accounts for the additional repulsion between the d electrons in the different d orbitals that sit in the same plane. All right. So, for example, dxy and dx squared minus y squared are in the same plane. So the repulsion between the dx squared minus y squared electron and the dxy electron is stronger than the repulsion between the dz squared electron and the dxy electron. Again, dxy and dx squared minus y squared d orbitals are on the same plane. But dz squared and dxy are not on the same plane. So in the latter case, you have weaker repulsion. So in the lectures, in the lecture videos, in the homework, you know the difference is 15B there. So 15B is 12,000 for this case. Question 14. Which of the following transition metal complexes is almost colorless? Well, this is one of the homework problems in which you need to explain why this is colorless, almost colorless. Hexafluorido, ferrite 3. So first, if you look at this ferrite 3, that means we have 8 d electrons minus 3. Okay, minus 3, because the oxidation number is 3. So we have a total of 5 d electrons. And then this is hexafluorido. Fluorido, that's a weak field ligand. That means we're looking at a high spin case. When you have high spin D5 transition metal complex, each d electron occupies a different orbital. So you have 1 electron in each of the 3 T2G orbitals and 1 electron in each of the 2 EG orbitals. And we need to maximize the spin for the ground term. That means in the ground term, we have a spin multiplicity of 6. And that's actually the only term with a spin multiplicity of 6. So when the electronic transition occurs, when this transition metal complex absorbs a photon and undergoes an electronic transition from the ground term with a spin multiplicity of 6 to a higher energy term with a different spin multiplicity, it's going to be spin forbidden for sure. And when you have a spin forbidden transition, it's extremely weak, and that's why this transition metal complex is almost colorless. Question 15. Which 2 of the following transition metal complexes have the most intense color? We're talking about charge transfer bands here. When you have a D0 electron configuration, the electronic transition involves charge transfer from the ligands to the metal, or from the metal to, when you have D0 electron configuration, it's the electrons must flow from the ligands to the completely empty d orbitals. All right. Anyway, this is charge transfer band, and then this 2, tetraoxidochromate with a oxidation number of 6, tetraoxidomagnate with an oxidation number 7. This one is called permanganate, I believe. So when you see a really, really high oxidation number, so first check if it's D0. If it's D0, then this transition metal complex very likely has a very intense color, because the photon-induced electronic transition of this transition metal complex very likely involves charge transfer. The electrons flow from the ligands to the completely empty d orbitals. Okay, you do not have any d electrons, and then, during the electronic transition, it must involve the electron flow from the ligands to the completely empty d orbitals of the transition metal center. Question 16, the smallest Rocca parameter B. So again, this B accounts for the extra repulsion or additional repulsion between 2 d electrons in 2 different d orbitals in the same plane. So when you have dxy and dx squared minus y squared electrons, they have a stronger repulsion. But when you have dxy and dz squared electrons, they have less repulsion. All right. So when you have a free transition metal cation, you have the largest difference between these 2 cases. So do not choose the free cation. So you want to choose the answer with the ligands that can delocalize the d electrons. The bromido ligands are called soft ligands. That means it's easier to change the electron distribution of the bromido ligands. And that means the bromido ligands can better delocalize the d electrons. That will reduce the difference in repulsion. Okay, two different cases. One case is dxy and dx squared minus y squared. The other case is dxy and dz squared. Okay, in the former case, there's a stronger repulsion. In the latter case, there's a smaller repulsion because dxy and dz squared are not in the same plane. All right. In this case, the bromido ligands help reduce the difference. The magnetic moment of a solid transition metal complex may likely decrease when a much higher pressure is exerted on the solid. This is because the high spin cases have a larger volume than the low spin cases. Under, if all other conditions are the same, when you have a high spin case, more d orbitals are occupied. When you have a low spin case, fewer d orbitals are occupied. Okay, let me give you a more concrete example. Let's look at a d5 electron configuration. In the high spin case, all 5 d orbitals are occupied. In the low spin case, only 3 orbitals are occupied. Only dxy, dyz, and dxz are occupied. dz squared is empty, dxy minus y squared is empty. So the low spin cases have smaller volume. And when you exert a high pressure to a transition metal complex, it's more likely you compress the high spin complex into a low spin complex. Question 18 is very tricky. If you answer this question incorrectly, don't feel bad at all. Because if you read the question, it looks all right. DD transitions are symmetry forbidden in this transition metal complex because the d orbitals all have the same G symmetry. It looks all right. First, if you have a cobalt transition metal element, either it's an atom or an ion, all 5 d orbitals have the G symmetry. Correct. And we know G to G transition is forbidden. Correct. However, this question is tricky because if you look at this transition metal complex, it's tetrachloridocobaltate. It's a tetrahedral structure without the G symmetry. So in this point group, it's a TD point group. There's no G symmetry. There's no U symmetry. There's no inversion center. So in this case, actually, all 5 d orbitals are distorted. They do not have exactly G symmetry or U symmetry. Okay, the 5 d orbitals overlap with the ligands one way or another, and that will distort the shape of the 5 d orbitals. They do not have the G symmetry. Okay, they do not have the G symmetry. In this case, the answer is false. And in this case, actually, this DD transition is symmetry allowed because it's not a GG electronic transition. I'm just trying to make sure that I answered all questions.